So we've seen that the GCD is playing a pretty important role. It's letting us tell when we can have multiplicative inverses, and this is very useful. So we need to be able to compute GCDs and be able to compute them fast. Now, the GCD is actually one of the first mathematical operations for which we have a non-trivial algorithm. More than 3,000 years ago, Euclid came up with something we call now Euclid's algorithm for computing the GCD. Now, you've all had a chance to play around with this algorithm, and what I want to do now is to analyze why does it work. How do we prove that it in fact gives the right answer? So we look at the algorithm, and it's pretty clear it has a recursive form. And whenever you see a recursive form, usually the way you want to analyze it is using induction. So how do we want to do induction on this? So the first question is always, what do we want to induct on? Because we have a pair of numbers, it's not clear what we want to induct on. So to do the induction, we're going to induct on y, which is the smaller of the arguments. Okay, so we're going to induct on this. So what's the base case? Well, the base case is y equals 0. So what we want to check is that this algorithm actually returns the correct GCD. So we have a GCD of x and 0. Well, for x and 0, the GCD is always x, because x divides both x, namely as x times 1 is equal to x, and x divides 0. X times 0 is 0. So this is equal to x, and so it's correct. So it works for the base case. So now we use induction. What kind of induction do we want to use? Well, we want to use strong induction, because we're going to get these smaller numbers that are x mod y, and they're not necessarily going to be the number right before y. Assume y, it works for some y less than or equal to k. So now we want to consider k plus 1. So when we run the algorithm on x and k plus 1, what's going to happen? Is y equal to 0? No, y is not equal to 0. So we're going to fall into this else. So what we're going to get is, it's going to return the GCD of k plus 1 and x mod k plus 1. So there's no problem with it returning this. It will return this. And this will be the correct GCD of those two numbers by the inductive hypothesis. What we have to do is to check whether it's the correct GCD for the numbers we want. This is what we have to show. If we assume that we know that d divides x and d divides k plus 1, we need to show that d also divides x mod k plus 1. So why is that? Well, the reason is that x and k plus 1, they're both some multiple of d. So this means d divides x means x equals f times d, and k plus 1 equals g times d. So we want to know about x mod k plus 1, which equals f times d mod g times d is equal to the remainder of f times d when you divide by g times d. So why is this true? Why is x mod k plus 1, which is the remainder of f times d divided by g times d, why does this have to be a multiple of d? Well, you can see everything here is in units of d. D is basically units here. So all that's happening here is a change of units. So what is f times d, the remainder after you divide by g times d? Well, that's just f mod g times d. So indeed, this shows that x mod k plus 1 is in fact a multiple of d. So because the divisors are not changed by modding one number by another, if they both have a common divisor, so will the mod of one by the other, this in fact returns the correct GCD of x and k plus 1, because we haven't actually gotten rid of any divisor. And in particular, if we haven't gotten rid of any divisor, we haven't gotten rid of the greatest common divisor. So this works. And so by induction, we've proved the theorem. What theorem? That this algorithm, GCD xy, returns the correct GCD.